Hello guys, my name is Jonathan Pack from Tongue New One's Chem 81 class of spring 2019. I'm just going to go ahead and walk through this chapter 21, activity 21, enols and enolates. So first it asks us to draw the two resonance structures, so I'm going to go ahead and draw them now. The first resonance structure can be seen with the double bond on the oxygen getting kicked up, which results in this molecule. I think I might have, no, we're good. And now the positive charge is here. So it's basically the carbonyl-carbon, right? That's the first one. And the second one is where this bond goes here, and this bond gets kicked up to the oxygen. Now this results in a structure where now you have a positive charge in here. 2, 3, nice. So this is where it will tell you the one. So the way you number this is you go 1, 2, 3, 4, right? And it's basically going to tell you whether it's going to do 1, 2 addition or 1, 4 addition. So it'll either add here, it'll either add here, or it will add here, as shown in this one. See how it's going to add here because the positive charge is there, right? Alright, let's just keep going. Now it's asking us to show the mechanism of the following transformations, but before that, let's read this right here. It says, basic nucleophiles like hydrides, so let's say LAH, or Grignard sources, any sort of MGBR, typically undergo 1, 2 additions, 1, 2 addition, and basically everything else, so that's your halides, your cyanides, your thiols, your alcohols, your amines, they all do 1, 4. Everything else. Okay, so let's just go through this real quick. The mechanism is relatively straightforward since it's the thiol, and thiols are 1, 4. Let's just go ahead and draw the mechanism for that. So with respect to the oxygen, you have to count 1 as the oxygen just to get everything straight. So you count 1, 2, 3, 4. That's how you would get this 1, 4 addition product, right? Now the mechanism is you have this bond, just draw it in green, going here, and this bond going here, resulting in this. There, and a positive charge. Now what you have is your sulfur nucleophile. This goes in, attacks. This results in this compound. Oops, I might have misdrawn that. There's 2. Now it's positive charge. Now what's going to happen is since this is an acid and you have some form of hydride source, this bond will come down, making this carbon here, this carbon nucleophilic enough to take this hydrogen. So now what you end up having is you end up having your carbonyl back, the hydrogen, I'm going to denote this in red so you can see it, this hydrogen, and now you have S, H2, H2, and now it just does the same thing. Takes the hydrogen, which leaves you with the product. So that's basically the mechanism. That's basically the idea. Now for the 1, 2 addition, since you're not really doing much, all you're really doing is you're just letting the LAH, which is the hydride source. Oops. We can think of LAH as basically just a hydride source. So we'll just say this is just H minus. And we're just gonna go ahead and attack here. It should come up right there. Now what you're gonna have obviously is you're gonna have this guy, right? And I'm gonna denote this new hydrogen in red. And now that you have a negative charge, you're going to have some form of water, right? Either some form of water, so OH2, and it's just gonna take hydrogen and then bounce off, and you will have this, an alcohol and an alkene. Oh. Now for everything else, it's just about doing, not really the mechanism, but just doing everything relatively quick. Oh, and this should actually be just acid. Acid works here too. Just withdraw that. OH2H. And the arrow, make sure you draw your arrows properly. Literally, this class is all about drawing your arrows properly. And there you go. Now everything else is just quick, fast, you know, doing it quick. So we see a cyanide, we see it's we go up, it's okay, it's not a hydride source and it's not a Grignard, so it must do what? 1,4 addition. So I'm just gonna go count 1, 2, 3, 4. So I know that my carbonyl stays retained, and I just simply get a cyanide group. Since this is the same strength as the Grignard, relatively similar, you're going to have that this will be a 1,2 addition. So what you end up having is you end up having the alcohol here. Maybe we have this, and then you have the methyl group. So if you were to just count it, it would be 1, 2, 1, 2 addition. Okay, let's go through NaBD4. Now, since it's also a good hydride source, it's deuterium, but it's just basically hydrogen with a bit more mass. We can conclude that it's going to do 1, 2 addition. So we count 1, 2, and then make sure on the carbonyl turns it into an alcohol. So you have an alcohol, deuterium, you have an alkene, and you have a methyl sticking on that. That is your product. Now for D, we have a thiol. A thiol, as we said before, is a 1,4 addition. So we can just count 1, 2, 3, 4, and make sure you're always counting towards the alkene in these kind of situations. Always, just make sure. So in 1,4 addition, we know that the carbonyl retains the carbonyl, and off of the carbon, we see that there is a thiol group. There you go. Now we have the same thing here, even though it's basically the same thing as, it's still a thiol nucleophile, a sulfur nucleophile basically. So you're gonna have a 1,4 addition. I'm gonna just show 1, 2, 3, 4. So we have this, retains the carbonyl, a sulfur with a methyl sticking out. Now for this one, I was actually quite confused on this one myself during the lecture, but it is very easy. Just look at it and you go, oh, that's the same thing as B, right? So you can just count 1, 2, 3, 4. So you just think of it as 1,4 addition, again, retains the carbonyl, and off this you have a phenol. Relatively simple. Now we have a Grignard again. A Grignard we know, as from previously stated up there, it is a 1, 2 addition. So be a 1, 2 addition. So 1, 2 addition. You retain the alcohol, you have the phenol, and then you have the alkene. Now lithium aluminum hydride is a very good hydrogen source. So with the very good hydrogen source, you're gonna do what again? You're gonna do 1, 2 addition. So you're gonna count 1, 2, 3, 4. So make sure you give the alcohol. Now this becomes the hydrogen, right? Goes down here, up, down. I'm just drawing the hydrogens just so you guys can see it as clarification. Okay, now let's go down to basically what the microdonor is doing. The microdonor's hydrogen is getting deprotonated, and it's basically being a strong enough nucleophile to attack the Michael acceptor either at the 1,4 or the 1,2 position. But you have, we'll learn later in this chapter or in this specific activity that there's a way to selectively make 1, 2, and 1,4. Well, let's just go ahead and do this right now. So we're just gonna see the mechanism really fast. This hydroxyl group is good enough to take that hydrogen, giving the carbon the negative charge, and with the negative charge, this is also going to be strong enough to make the 1,4 product or the 1,2 product. It doesn't really matter, but there are ways to specifically make this product. So this is also very easy. You're basically going to do the same thing as you did here, right? So you're going to have your microdonor. Just draw your microdonor out first. And then you know the hydrogen is going to be deprotonated in the middle. just because that's the easiest hydrogen to take, and it also has the most negative charge because it has the most resonance, right? You can resonate it twice, so it's very resonance stable. So you have this, you have a microacceptor, so you know 1, 2, oh my god. 1, 2, 3, 4, right? So you just draw the bond. 4 has a methyl group sticking out, which is then bonded to. So just 1, 2, 3, 4, 4 and 3, and 3 is connected to 2, which has a carbonyl on it, and 3 is also connected, which has a methyl on it. That's how you should think about it for most of these. Same thing for this one. We're gonna use the hydrogen in the middle. So we have this, right? 1, 2, 3, 4, right? So we can literally just draw this. 1, 2, 3, 4, and carbonyl. Cool. Easy. Same thing for this one. I was very confused when I saw this reagent in lecture, and I didn't fully understand it, but it makes sense to me now. It's just basically you have a Michael Donor-Gilman reagent, and what this will make is this should make a product that looks just like this. Oh, not sure what's going on. And remember, this is also 1, 4 addition, so you count 1, 2, 3, 4. So the right side is remain completely untouched. I mean, yeah, the right side remain completely untouched, resulting in this product. And it's an ethyl, so you're basically adding an ethyl at a 1, 4 addition. So count 1, 2, 3, 4. So 2, 3, 4. Ethyl is 2, 5, 6. So it should be 1, 2, 3, 4, 5. There you go. Now for the nitro group really doesn't do much here. You're just gonna have the same thing again. It's just gonna be this hydrogen, because it's a nitro group and it's electron withdrawing. You're gonna have that hydrogen being protonated by the hydroxyl group in this reaction, which is in this case is NaOH. So you're gonna basically have this. This is the point where it happens. Now this is also again 1, 4. Just go ahead and draw the cyclohexane, and from here you just have to be careful with the numbering. You know, to attack this position, so it's 1, 2, 3, 4. So you would have to. Oh no. So it would be. Don't know why it's randomly disappearing. 1, 2, 1, 2, 3, 4. So because you count the oxygen, right? So, oh. There you go. Because you want to have it 4 from the oxygen, or for 1, 2, 3, 4. That's your product. What starting materials are required to prepare the following products? Now this just goes back to, I think there's a squiggly line thingy you can do, and it basically just makes life very, very, very easy. So all you need to do is you just need to cut the compound at this specific point right here. Give this guy, give this anhydride its thing back, and then give this guy its Michael donor back. So you're basically making the Michael acceptor, a Michael donor, and the Michael acceptor. That's basically all you're doing. And you can use, for this one, I think you can use sodium hydroxide. Sodium hydroxide, which will work just fine. So, NaOH. Oops. Now for this one, it might look a little tricky and maybe a little bit daunting, but if you break it apart into its components, it becomes relatively simple. So, see, like this part, doesn't this look like kind of like your Michael donor? It looks kind of like your Michael donor, right? So what you're gonna have is, you're gonna just cut it up here. pH, right? Plus, and 1, 2, 3, 4. So I'm gonna just draw that. Oops. Whoopsie daisy. I'll draw it like this. Might be easier for you to see. 1, 2, 3, 4. And then there's a double bond right here. So 1, 2, 3, 4. There you go. And this, I'm pretty sure you can use sodium hydroxide again. So I'm just going to write sodium hydroxide. There we go. And now for these one, since there's a methoxy group sticking out here, you're going to have to use NaOMe as your base. So basically, you can just see here, this CN group is clearly going to be the electron withdrawing thing that's going on here. So you have to pick which one's going to be your microacceptor and which one's going to be your microdonor. So you just kind of go ahead and cut this bond up right there between the carbon and the 1,4. Like, what kind of looks like 1,4, right? So you just go 1, 2, 3, 4, and you're like, oh, okay, I see my microdonor and my microacceptor now. So what your product ends up, well, not your product, but your reagents are going to be this, and you just count 1, 2, 3, 4, boom, and then you put the double bond between 1, 2, 3 and 4, and you're good. You're good. Oh wait, hold on, let me read this. What? One, 2, 3, 4. Woo! 1, 2, 3, 4. So you count 1, 2, 3, 4. Boom. And for this one, since you have a methoxy group here, you want to use NaOMe. You want to stay relatively similar to your substituents, if I am not mistaken. I don't think I think for those you could use, yeah. I think that's relatively certain. That's why you use NaOMe. All right. Now for this one, we see that this here is probably going to be your Michael donor. And this is going to be a Michael acceptor because it's adding at the 1, 2, 3, 4 position. Now you just cut this guy up and you have your anhydride. You have your anhydride and you have your cyclohexane. 1, 2, 3, 4, 6, boom. And boom, that's your product. And for this one, you want to use NaOMe. There you go. And that's how you do the microdonor and microacceptor parts. Now, the way we make exclusive 1,4 addition products comes by something called Stork Enamine reaction. And what this is doing is you're making a enamine. And with the use of an enamine, you can exclusively make 1,4 addition products. So there's a whole long mechanism. Grab some popcorn because you're probably going to need it. It's going to take a little while. Alright, so let's just go ahead and get right into this. I'm going to use a thinner pen so I can actually write the entire mechanism out. So we're just going to go ahead and first start with the deprotonation of the hydrogen off the hydronium ion. This, boom, boom. Now what this is going to do is this is going to make my carbon here more electrophilic enough. Now since this is a secondary amine, it's not actually strong enough to just go in by itself and attack, unlike a primary amine. So we're gonna have this thing, this guy is gonna attack, and that's gonna kick up. Now we're going to have this product. It's intermediate, I'm sorry. And we're going to have a nitrogen who has a hydrogen attached with a bunch of other things attached. Okay? Now, from here, since the nitrogen still retains its positive charge, right? Because 1, 2, 3, 4, that's, we're going to have, in this case, just water. Take the hydrogen and give nitrogen the lone pair back. Now what that's going to do is that's going to allow for the creation of the enamine. Creation for the enamine. And first, before we do that, we need to make this alcohol a good leaving group. So what we need to do is we have to remember this stuff is very important. Alcohol is not strong enough to leave in this situation. So you're going to have a water and nitrogen. And what's going to happen is 1, 2, 3, 4, 5. Let me just make sure I'm counting the numbers right. 1, 2, 3, 4, 5. This lone pair is going to kick down, kicking this water out. Now, this is where you will finally have something that looks similar to your enamine, but not quite there yet. You will have this hydrogen here. The hydrogen right here is going to be taken, abstracted by, let's just say water in this case again. Whoa, why is it green? Water takes it, which gives this carbon its bond. And so what's going to happen is this guy's going to go here, this guy's going to go up. And now, as a result, you will finally have your enamine. Now, with your enamine, then you can make this your Michael quote-unquote acceptor. Michael quote-unquote donor. And then what this will do is will come down and give that carbon the electrophilicity the nucleophilicity it needs to create this specific product. Now we're going to have this as our thingamabobber, as our other reagent. Now what's going to happen is this guy's going to go here, and this results in this product. There are quite a lot of steps to this, so bear with me. Boom. Okay. And just to reiterate, to show you the movement of the double bond, this double bond will go here, this will kick up. That's basically how the arrows should look like. And now from here, we simply just grab the hydrogen from the acidic solution, which basically makes this an alkane. So what this does is it goes down, and upon doing so, this alkane takes the hydrogen, that gets dropped off. Now finally you have this. Now that we're here, we're going to have water come in, attack this, kick this guy up, and now the idea is to make this nitrogen, this amine, a good leaving group. Now what you're going to have is you're going to have this product. Nitrogen, low hat, and OH2. That's going to get deprotonated once. Another water just going to take one of those hydrogens, give that guy his bond back. Oops. Oh man, this mechanism is very tiring. One, two, three, four. Oops. 1, 2, 3, 4. 1, 2. I need to make one more carbon in there. 2, 3, 4, 5. Okay. Now we need to make this nitrogen amine a good leaving group now. So we have this in acidic conditions. Don't forget. Oops. Oh my god. This is so tiring. I'm just kidding. Now we have this guy in acidic conditions. I don't need to draw that. Boom. This guy's like, whoa, give me that. So it takes the hydrogen. Now this becomes S. 3, 4. Boom! Now this is a good leaving group finally. This kicks down and this gets kicked off. Oh! Now this forms your carbonyl and this hydrogen here. Remember, there's a hydrogen because this is an alcohol. This hydrogen gets a positive charge, and water is like, woo, give me that. And now you finally have your product plus this secondary amine used for the Stork Enamine reaction. Now, if we look at our starting, this was our reagent. Basically, this is what we had. And we wanted to make it exclusively 1,4, so by taking this hydrogen out, we want to have it there. So this and that indeed, let's count the carbons. Carbons 1, 2, 3, 4, 5. Carbons 1, 2, 3, 4, 5. Boom! That is the product. Now it looks exactly the same, and that is how you do the mechanism for that problem. Now let's just continue, keep moving on. Go back to the Word doc. Now that we've gone over the Stork Enamine reaction and we've gone over the mechanism, now we know that the Stork Enamine makes specifically 1,4 exclusive products when reacting with a methyl donor and a methyl acceptor. So now let's just go ahead and start. These are things you should practice, and these are things you should memorize to assist you. And since this is 1, 2, 3, 4, we're just gonna go ahead. So it's 1, 1, 2, 3, 4. Boom. That's your product for one of them. And now for this one, first obviously you're going to need some sort of, I guess you could just write R2 because it doesn't really matter what you have. You just need some sort of secondary amine. And now we see that we want a 1,4 exclusive addition. So we're gonna see, oh, what does this look like when I grab this guy and I cut it up here? And boom, there's your product. There is your thing. So this, what is this gonna look like when I cut it up there? And you're just gonna have boom, 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 3H3O plus, always an acid. Cyanide, it's relatively electron withdrawing, which leads me to believe that this is probably going to be your Michael fucking, oops, that's another. Now for this one, we can just simply cut it up here, and we'll get this as our starting reagent, and this would simply just be this. Okay, now for this is all synthesis. These are things that you should have learned how to do up until this point. It should be relatively simple. I'm just gonna go over with you how I would approach these problems. Maybe it might make it a little bit easier, it might make it a little bit more difficult. I'm not exactly sure. But what I do know is that you're gonna have a great time, and that's all that matters. Guys, now that we're finally here on question number 8, we're just gonna synthesize the following targets. This is just gonna be things that you should have learned in lecture up until this point, and it might be a little bit difficult in the beginning, but eventually you'll get it and it won't be a problem. So the first thing I'll do here is I'll think, oh, how do I want to make a double bond here? How do I want to add a double bond so I can use maybe some sort of a, a Gilman reagent or a Gilman reagent, and to make the 1,4 addition product, because you see how it's going from here. If we count, it's 1, 2, 3, 4, right? So we somehow want to make this. That's our target. So what I'm going to do here is I'm going to use, from the starting molecule, I'm going to use acid, bromine, and pyridine. Now what this is going to do is this is going to make this guy. That's what we want. We start obviously with this. Now from here, since I want to use a 1,4 addition, I don't want to use something strong like a Grignard. I want to use like a Gilman reagent, which should do 1,4 addition. The pH2, copper, lithium, and I believe acid. And this basically makes your product. Well, just draw it again. Basically makes your product. Cool. Okay, now for this one, this is kind of hard. I mean, it's not hard, but it looks like there's a lot. But we're just going to start with the first things first. We have this simple cyclopentane. We're going to just brominate it. I like using BRHV. Oops. I'm not an MBS kind of guy, you know what I mean? So we're going to just use BR2HV. Give you this bromine basically anywhere on the ring. Now from here, we're actually trying to make a ketone first, right? And by using the ketone, maybe we can do some sort of Stork Enamine reaction just to exclusively make this ketone into a 1,4 addition product. That's basically how I'm thinking of it. So I'm like, okay, how do I want to make this? I have a good leaving group now. All I need to do is do some sort of elimination reaction, right? And then boom. Am I very damaged? So what is this? 37? 37. So for problem number B, it might look a little daunting at first, but the first thing you want to do is you want to think of how you can make a ketone. So just don't even worry about this whole side here. That whole side's fine. That's not a problem. What you need to think about is how are you going to make this molecule? And what you can do, right? The first thing that I would do personally is from this molecule, maybe I can brominate it. And when I brominate it, this is my product, right? It doesn't really matter. And then maybe I can just do a simple elimination with sodium hydroxide. And that should give you, we'll just draw it under here. It's a little cramped. NaOH. Boom. Now that's what you have. Now from here, doesn't really matter what you do. There's no reason to have, you know, a more substituted side because everything is equally substituted. So you can just go ahead and use acid. And this is alkene chemistry in chapter 9 or chapter 8, I believe, of Chem 80. You should go ahead and review it if you haven't. And what you're going to have here is you're basically going to have an alcohol. And you learned this before. And how do you turn an alcohol into a ketone? You can either use Jones reagent. Since it's a secondary alcohol, you can use Jones reagent or you can use PCC. It doesn't matter. For this reagent, I'm just going to go ahead and use PCC. Boom, that's your ketone. And now from here, how are you going to make it exclusively one? Because I mean it's 1,4, right? 1, 2, 3, 4. So this is easy, right? 1, 2, 3, 4. Boom, like that. That's the easy part. Now the question you have to ask yourself is, how do I make it exclusively 1,4? We just learned moments ago that in the Stork Enamine reaction, we only have 1,4 products. So all you really need to do is you just really need to just literally use any random secondary amine. Boom, that's your secondary amine. Doesn't matter. And then from here, you just use acid. Oh, I forgot the number. Remember, you should always number, and then you get your product. Relatively simple, but don't take it lightly. Don't take it lightly. Just always be ready. Alright, so for this problem, this might look very difficult. You're like, what's going on? But the solution's actually relatively simple. So the first thing we're going to do is we're going to think, how do we add a methyl to the 4 position with respect to the oxygen of the carbonyl? And how do we add a phenyl? A carbon with the phenyl attached. So we can just work backwards maybe, right? We can maybe think, oh, it might be some sort of nucleophilic attack or, you know, something like that. That's kind of the gears that I want you to think of how you can approach these mechanism problems, or not the mechanism, synthesis problems. You want to think about the products, you want to think about the substituents, and then when you can bring them all together, then the product should be relatively easy to form. So the first thing I'm going to do is I'm just going to start by adding a methyl to the 4th position of this pentene cyclopentenol. No, that's not all. I can't name. I'm sorry. I give up. Anyways, so we have here, what could we do to make this 1,4 addition exclusive to the methyl? So then we just use a Gilman reagent again, right? Use the Gilman reagent, and you just have this guy. Amine. Whoa! Whoa! That's what you have, right? And now from here, you have the idea that, okay. Remember, when you do 1,4 addition, wait, how does that negative charge get there? Yeah, so the first thing you want to do is you want to have this 1,4 addition kind of idea in there. So what the first thing I'm going to do is I'm just going to redraw my reagent. That looks really bad. And I'm just going to use a Gilman's reagent. Me2 copper lithium. And this should make this. And now from here, this is one of the intermediates of the reaction. This better helps should visualize how you're going to get this product. Now this bond goes here, this bond goes here. This negative charge is good enough to attack. And since this is only a secondary alkyl halide, it should be enough for the reaction to actually happen in an SN1 or SN2 fashion, probably an SN2 fashion. Well, actually, since this reaction is a primary... Since this reaction is a relatively less hindered alkyl halide, it should go in a nucleophilic attack position. So what you're going to have as a product is this. Boom. Thank you so much for watching. I hope you all learned something and you can take away something very important. And have a great rest of your semester.